Hello, today we're going to look at curved or warped space-time. What gives us a clue that space-time might be curved? Well, in our previous videos on space-time, there are two clues that we might have spotted. The first is that if we draw a space-time diagram, that is, time placed against space, and as usual we'll just do it in one dimension in space and one dimension in time to keep things simple. If you draw an acceleration in space-time, the curve looks like this. What it means is that for any incremental unit in time, the distance that you travel is progressively further. All this is really saying is that as you accelerate, you go further, faster, because you're speeding up. But that curve is a curve. And that's our first hint that we might have some kind of curvature in space. And the reason for that is the principle of equivalence. You'll remember that Einstein had said that a person standing in a box on the surface of the Earth, but subject to the gravitational attraction, is equivalent to a person who is in outer space in a rocket. Here's the fuel, travelling or accelerating at g. And Einstein says those two things are equivalent. There is nothing that anybody inside that box could do to demonstrate whether they were either stationary on the Earth subject to an gravitational force g, or accelerating through space subject to an acceleration of g. Now, a person who is accelerating through space will travel through space-time on the basis of this diagram here, like that. That is their journey through space-time, if they are accelerating through space at g. And by the principle of equivalence, that must mean that the person who is stationary on the Earth, but subject to the gravitational acceleration, must also be travelling through space-time, even though apparently they're not moving, according to that curve. The second clue that we had in our previous videos is just in relation to the space-time diagram where you travel from this point here, which we'll call point O, to a point P. We have travelled a distance x in a time t. But the problem is, of course, that another observer who is travelling at a speed relative to us will not measure the same x and will not measure the same t. That's the problem. But what we showed was that there was one value that everybody agrees on, and that is that s squared equals c, the speed of light, times t squared minus x squared. So whatever values of x and t anybody measures, if you put them into that formula, they will all agree on the value of s squared. But we've never actually said what s squared is. Well, ct is a measure of distance. Speed times time gives you distance. And x is also a measure of distance. So s must itself be a measure of distance. And s is in fact the path through space-time. Now, at first thought you might have expected that the distance through space-time of travelling from point O to point P, if that distance is s, then you might say that that ought to be, this distance here of course is ct, we always multiply by c so that we've got the same units in the time direction as we have in the space direction, so we can compare like with like, otherwise we're doing apples with pears. You might expect that s could be described quite simply as s squared equals ct all squared plus x squared, which is just Pythagoras. But in fact, the correct term is s squared is ct squared minus x squared. And that's our second clue, because if you plot that on a space-time diagram, what you actually end up with is what they call Minkowski space, where every point on that hyperbola satisfies this equation, s squared equals ct squared minus x squared. But here's the problem, that length and that length and that length and that length and that length are all different. And yet we're saying that they are the same. And that suggests that this representation on a flat piece of paper isn't quite correct. So now we say that if acceleration through space has a curved effect on space-time, and gravity by the equivalence principle also has a curved effect on space-time, then we need to ask ourselves the question, what causes gravity? And the answer is mass. And so we come to the conclusion that mass warps space-time. And its effect is to cause any body to follow a straight line which is curved by space-time. It's a little difficult to draw for someone like me who isn't really an artist, but if this is what one might call flat space-time, then the idea is that a mass actually causes that space-time to dip down. It's rather like standing on a trampoline. You depress the area where the trampoline is, and so you cause a bit of a dip in the trampoline, in this case a dip in the space-time, so that a particle, even a particle of light coming along, will think it's continuing in a straight line but will be diverted around. Imagine a golf ball that just skirts the edge of the hole and diverts its direction as a consequence. That's the effect of gravity. I can try to describe it another way. Let's just think about the Earth for a moment. And the Earth has lines of longitude, which are great circles going around the Earth. There's also another great circle, which is the equator. And what we're going to do is we're going to get two people to start out on different lines of longitude. Each of them is being told to face due north, and each of them is told to walk in a straight line due north. And so each of them begins to walk along the line of longitude. Now what will happen as they walk along it? They will find that they are getting closer and closer together. And if they don't know why, they might come to the conclusion that there is a force which is attracting them as they move. They're both moving ostensibly in parallel lines due north, and yet they are being drawn together. Indeed, when they get to the North Pole, one will be facing in that direction and one will be facing in that direction. Yet they both started out facing due north, and yet when they get to the North Pole, they're actually at an angle to one another. And that they can ascribe to a force. But in fact, it's not a force at all. It's just the consequence of going round a curved surface. They travel in straight lines, parallel to one another, and yet they are attracted together. This illustrates the principle of curved space. So effectively, Einstein's theory of general relativity says that gravity doesn't actually exist at all as we understand it. It is an illusion. The illusion is caused when we follow a straight line in curved space.